Hey guys, Quiff the Lazy Geek here, and let's do some quick processing video on the Elephant Trunk Nebula that I got in my last video that you may have seen, and I'm leaving a link up above, taken from my Tokyo balcony, just as usual. Now, I'm going to use PixInsight as always because that's the tool I am the most used to. I have yet to try again Star Tools and APP, sorry, AstroPixel Processor, and I am not familiar at all with Photoshop, and maybe one day I'll try to do processing with just free software, but for now it's PixInsight. PixInsight is expensive, but it is worth it. I bought it 4, 5, 6 years ago. Never let me down. It's an awesome piece of software. Anyway, let's get started. We haven't got all day. Okay, and we are in PixInsight. We're going to start by stacking stuff, right? So I'm going to go under script batch processing, weighted batch pre-processing, and then we're going to select the various frames that I took. So the light frames are the frames that I took of the actual target, which is this one. So I'm just going to add all of my light frames without any consideration for anything. Now, for now, I am not going to stack the frames, so I'm going to calibrate them only. I could do that manually very easily, but I just happen to be lazy, so I rely on the script. Then the same thing, I'm going to add flat frames. So my flat frames, they're actually in a different folder. They're here. We're going to add my flats. And I am going to add my dark frames, which are here as well. So I'm going to add my darks. Which I believe, 300 seconds and 180 seconds. That's the both I need for my H-alpha and O3. I do not add bias, but I will add dark flats as well as a dark. So if you don't know what I'm talking about, it's all about calibration frames. You have light frames, which are pictures of your target. You have dark frames, which are basically like the shutter closed and the sensor taking an exposure of the same length as the light. You have flat frames that model the optical aberrance, the optical issues of your system, like dust motes. And then you have dark flats or flat darks, or some people call them tomato frames, that that are dark frames for your flat frames. And you also have bias frames, but I don't use those. If you're curious about what is what, go and check my video about calibration frames. It's not that complicated, and there's a great little slide deck summary in that video as well. Okay, so now that we're ready, I've added darks, I've added flats, I've added dark flats, and I've added my lights. I've said that I want to calibrate only, so I'm keeping like the defaults because I'm too lazy to play with those, and I'm just going to select an output directory, and I'm going to call it processing Elephant Trunk 2 because I already did it once, but let's do it again just for you. Cool. Okay, and let's get this show on the road. Let's get it started, and we'll just wait until it's done. So see you then. Okay, and the script is done. So now we have calibrated our frames, both H-alpha and O3, which are both monochrome kind of frames. We'll end up combining them for a color image. But for now, we're going to go inside the process that's called the SubFrame Selector. That lets me basically remove frames that are no good, or put a very low weight on the frames that I don't really like, but that can still contribute to my total signal to noise ratio. The first thing we're going to do is measure our subframes. So I'm going to go under Add Files, and what we're going to do is I'll make sure that I am indeed in the calibrated folder. I am going to select all of my H-alpha because I don't want to compare H-alpha and O3 together because the nature of those frames can be quite different. I'm going to kind of like ignore everything in there except put 16-bit as the camera resolution. Doesn't really matter unless you want to know what your actual full width half max in terms of arc seconds is actually. I don't really care, so I'll just leave those values as is. If you have no idea what full width half max of our FWHM is, I have a video on that topic if you are interested, and I'm linking to it up above. Okay, so we will be measuring the subframes, so let's get started. So now that the frames have been measured, we're going to look at basically I'm going to use my main criteria will be eccentricity to make sure that I remove like really bad frames. So I'll just remove like eccentricity, I'll put under approval, I say that eccentricity, just use the name as is, should be less than 0.7. So that will be one of my approval criteria. And that's it. And another one I can look at the FWHM, which is not the real FWHM in arc seconds. It's actually right now in pixels, really. And I'm not going to exclude anything based on the FWHM directly. I'm going to look at my number of stars, and we can see that it basically gets higher as we get closer to the meridian, as we get closer to the highest path in the sky that the target takes. So we'll want to put more weight when there are more stars and less weight than when there are fewer stars. So we're going to do something a bit stupid. I'm going to do something like stars minus 300, like roughly like the minimum. And we're going to divide by stars max. So any of those criteria, you can write the name. So here we have stars, and add something like max or min at the end. And when you click here, it will apply the weighting, and you'll see the weight appear here. And we can see the lowest non-rejected weight. Actually, I need to sort by weight. Okay, and the lowest non-rejected weight is 0.3, and the highest is 0.7. Which means that roughly the lowest weight is counted half as much as the largest weight, which is more or less what I'm after. So it's like if I don't get exactly the right number, I'll just like play with this, because I don't like complicated formula that just work from the beginning. I'll just do an iterative approach until I get weights that kind of make sense to me. These weights here, well, they kind of make sense to me. We could try to go from to 1 by just, instead of using stars max directly, go stars max minus 300 and then play with that. That works too, and then we have 0.437 to 1. That works as well, and we can use that as well. Not a problem, and just playing with those two numbers can get me good results. So now that I have my frames with the proper weights, I'm going to say output subframes, and I am going to select a folder where I will have, why do I have a debayered folder in there? This is monochrome data. Where I will have a folder called measured, at least for me. So I'll create a folder called measured, I select this folder, and then I'm just going to record those frames. And now I'm going to do exactly the same for O3 very, very quickly. So I'm going to add the files. This time it will be O3, so we can always compare apples to apples. We're going to validate that. We are going to measure the subframes. And we'll wait until it's done. And we're done, and we can see the same thing. We can see exactly where the meridian was. Because we get the most stars. It's so silly to look at this like that. And the meridian, by the way, it's the reason why I like to do a meridian flip, because otherwise I can take advantage of only one side of the best part of the image for me. I want to take both sides. That really does good things for my signal to noise ratio. At any rate, we can then look at the eccentricity. And yes, I think we can remove that one picture that went all over the place. And we can look at the full width half max. Yeah, whatever, acceptable. Maybe I'll do, I won't do anything. I'll just do based on the stars. So with my current weighting criteria, I get from 0.6 to 1. I want to have a slightly bigger spread between 1 and the lowest, so I'll try various values. Okay, and this works well for me. We have weights that range from 0.5 roughly to 1, which means that the lowest will be counted half as much as the highest, which is good enough for me. So I am now going to output my subframes just like we did before. Very easy, very fast. Okay, and we're done. So we have now basically we have calibrated our frames and we have measured our frames, so we know how much we want to take them into account. Now, one of the things that I forgot to do with the SubFrame Selector, so I'm going to reopen it, is find out which frame was the top frame for me. So the top frame for O3 was 0034, so let's write down somewhere. number 0034, and I can double check it and see whether it has any gradients. And the star shapes are not great, but I don't care that much. It does not seem to have very obvious gradients, so we can use a process called local normalization based on that. If I add my H-alpha again, I think it remembers the measurements. And indeed it does. We can look at the picture with the most weight, and that picture seems to be 0022. And if we look at this, we can see it's this one, and I do not see any obvious gradients, which is good. It's not strictly necessary for narrowband, what I'm going to do next, but you know, it can help. So before I do what I mentioned, we're going to register the frames, meaning we're going to align them together based on their stars, like the position of their stars. And if there's a bit of a difference between the frames, then they'll be like kind of like moved around until they can be stacked. So for that, we're going to use the star alignment. And we're going to use the reference image, whatever we have for these. So I'm actually going to use H-alpha as reference for everything. That way we'll have all of the images actually aligned to that particular image. So H-alpha 0022 is what I will be aligning everything against. And then I'm going to select all of the pictures that I have measured in here. So we will be aligning to this image all of the images, both H-alpha and O3. The output directory, I'll create a new one, and I'll call it registered. We're going to select that, and we're going to launch that. Okay, and our star alignment is done, so we can go to the next step, which is optional, which is the local normalization. Now, local normalization, basically, it uses a reference frame to perform some kind of like automatic background extraction from each of the frames individually. And that can help a lot in reducing gradients in the final image, so it can be quite useful. It is not something that you want to do for everything, but it is something that can help, but it will only be helpful if you have a picture without gradients. If you have a picture with gradients that you use as the reference, you'll just like mess up all of the pictures with the same gradient, something you want to avoid. So we're going to go into registered, and for now we're going to set our reference image for H-alpha, which is number 22, as we saw from our weighting. And we're going to add the H-alpha frames, because we need to do it filter per filter in this case. And we're going to leave the output directory blank. This does not create new images file. It creates local normalization files, which are basically text files. And we're going to let it run on that. We're done for H-alpha. Let's repeat exactly the same process for O3. So the O3 image number is 34 that we're going to use as a reference, which, if I remember correctly, did not have a lot of gradients. We're going to validate that, and we're going to add the O3 frames only this time. So let's go O3, select everything, and launch it again. And we're done with that local normalization. So now we have everything done. So we've calibrated, we've measured the subframes, we've registered them, so aligned them together. We've done local normalization, which is optional. Now we can go inside the integration. So image integration, we go in there and we're going to add, first we're going to do the H-alpha frames. So I am going to go under indeed registered, and I'm going to add all of my H-alpha frames here. And I'm also going for me to add my local normalization files for H-alpha as well, which were created. Then I can choose my combination. So combination average, that's fine, but normalization, while I could normally leave it as it is, here we're going to choose local normalization because I chose to use local normalization. The weights will not be noise evaluation, but we're going to use the fits keyword that we had in the SubFrame Selector, which we can see is SS weight. So we have it as SS weight in here. Now the pixel rejection, I typically use Windsorized Sigma clipping, and I uncheck clip low range, and I use here local normalization. I don't remember exactly what I would use otherwise, but right now we have local normalization files, and this is what we are going to use. I typically don't change the pixel rejection options because they seem to work fairly well for me. And then I can just let H-alpha be integrated. And we're already done with H-alpha. We can have a quick look at how it looks like. It looks good. Sorry, it looks quite good. Let's do the same for Oxygen 3. So we select all of our Oxygen 3 files. We also select the local normalization files for Oxygen 3. We're not going to change any of the other options, and we're going to let it do its job. Okay, and Oxygen 3 is done as well, and actually it doesn't look too bad at all. So, yep, we have H-alpha, we have Oxygen 3, so our pre-processing is done. So now we can go into the actual post-processing of the image. So let's get started. So first things first, I will want to crop my images so that we have a same frame of reference between the two. So what I'll do is I'll just open the dynamic crop tool, and the image that seems to have like the most black borders is this one. I'm not sure why I have a bit of rotation. Maybe my polar alignment was not as good as I thought it was in here. But anyway, we are going to select this, and then I'm going to apply that to the H-alpha image and then validate that for the O3 image. And now we have the exact same field of view for the two. The next thing is simply like a matter of convenience for me. I'm used to seeing this image on the upside down, so I want to just rotate both images by 180 degrees using the rotation tool. Fairly simple. Now the next step is going to be using the easy processing suite created by DarkStructureEnhance, which I have presented in another video, which you can check here. I'll also be leaving a link down below about how to actually, where the link is. But all the instructions, you'll need to add a repository, so for that you need to watch the video if you don't know what to do. Now in this easy processing suite we have easy decon, which is basically a way to get more details out of your nebula or galaxy pictures. And I'm not going to run it on Oxygen 3 because it does not have a lot of details to eke out, but I am going to apply it to H-alpha. So H-alpha is called integration. So we first need to create a star mask. So I'm going to click on create new star mask, which uses StarNet++. So again, if you don't have that, you really want to check my video on that first. But it takes a few moments to generate that star mask, and then I chose to do it with the raw star mask because I'll be boosting the stars in that star mask manually. So here we are. I'm going to look at the star mask itself, and then I'm going to say SCF stretch to have the stars a bit more visible. We're going to boost them a bit, and we're going to dilate them a bit to have a proper star mask. And this will probably work pretty well. The next part is I want to generate a PSF, which is, I don't even remember what it stands for, parametric something. And that will basically is the overall star shape in my image. Just clicking on generate PSF does it for me. And then I've always found that for now the default options work very well for me. Now if I wanted to be very careful about things, I would actually create a preview on my H-alpha frame. Then I would evaluate the easy decon on that preview before doing it on the real image, but I'm just going to do it on the real image directly. And here we are, it's done. So I'm not going to show the before and after. This is a quick processing video, but there is definitely more detail than there used to be. You'll want to check the before and after for yourselves, but otherwise, this seems to have worked fine. I'm going to close the star mask. I'm probably not going to need it anymore. I'm going to close this as well. Well, we can still have a look at before and after. So the before is this, and the after is this, and we can see there is definitely more crispness to the image without really increasing the noise, which is very, very welcome. The next step is using the easy processing suite. I will do some easy denoise, And the easy denoise for me, it works quite well on both H-alpha and O3 with my TGV settings set to 0.5 and my MMT settings, all of them set to 0.5. At least that works well for my images. Again, you'd want to use a preview to evaluate the easy denoise run before actually running it, because it takes a bit of time, but I'm just going to run it directly on the image, and I'll do the exact same thing for the Oxygen 3 image as well. Okay, and both images have been denoised with various degrees of success. So, you know, before denoise, after denoise, and same here. So it looks like, especially the O3, the result looks quite good. I would need to remove the masks to actually show you how this looks. I'm just going to close the mask references so you can have a quick look at those. Okay. So let's have a look at the before and after. So this is before, this is after. It might not be so visible on the video, but to me the difference is very large. Yeah, much better. This is a great script. And now we're gonna still go into the scripts and we're gonna do soft stretch for both images. So we're going to go inside integration and we're going to say run easy soft stretch, and we're going to do exactly the same for easy processing suite, easy soft stretch of the O3 picture. And that basically stretches the image. So neither image is linear anymore. So now we've made the images something that we can process with non-linear processes. So the advantage of using this soft stretch is that the images end up having basically the same mean/median, so I can combine them directly. And what I did for this one is I went into Pixel Math, although I could use LRGB combination directly. And under Pixel Math, first I renamed integration 1 as O3, and then double clicking I will rename integration as H-alpha. And under red I'll put H-alpha. I'm going to uncheck use RGBK as single expression. We're going to use O3 for both green and blue. Then under destination, I want to say that I want to create a new target image, and the color space will be RGB color. Then I click on this square here, and this will create a combination of those two images. And we can see we have some color already, but what I also like to do, that color is a bit too aggressive, and I want to get more detail. I'll go into LRGB combination. I'm going to uncheck red, green, blue. I'm going to go inside L as H-alpha, so that means we'll use H-alpha as a luminance source for this image. And I'm not sure whether I should check or uncheck chrominance noise reduction. I ended up doing it, but you know, doesn't make any difference. I have no idea. But we'll end up with a color image that I am going to work with. And here's how it looks like. So we have very smooth colors. That image on its own is already, like, as far as I'm concerned, it's already really good. Now we're going to play with it a little bit though, to make it look even better. So the first thing I'm going to do is I'm going to do a run maybe of SCNR, which will remove the green from that image. You can see the stars here have a green tint. So we're going to remove that green tint here. Now that we have removed the green tint, I am going to apply some curves. So I'll go inside Curves Transformation. Here it is. And I'm going to open a preview using that preview button. And we're going to apply like some light curves to make that image a bit brighter. We might enhance the contrast a slight bit by pulling down at the very bottom of the image. So this is before, after, maybe a bit more on the bright side. And here we are. We're getting already like a bit more visibility into the image. Okay, and so now that we have this image, what I'll want to do is probably like increase the blue saturation for those little areas that are in between this kind of like brownish dust on the image. And if I do that, it will actually also like increase the saturation of the stars a lot. So what I could try to do is remove the stars, process the nebula without the stars, and then add the stars back, if that works. So we're going to try that with StarNet++. I'm going to make a clone of my image, and a black and white version of my image. I've never really actually, I've never done that before, so we'll see how well it works. I'm gonna create a star mask based on the black and white image. Do I even need a star mask? No, I don't think I do. And no, actually, no, I don't think I need a black and white picture. So one of those pictures, I'm just going to remove the stars. And the other, I'll be just creating the star mask so that I can then add the stars back later on. I guess that's how it works. We'll see if that's really the case. We'll see if it really works. I've never done this before. Okay, so now we've removed the stars. I'll make sure that we have the star mask in the picture right next to ours. Should give me exactly the same results since those are the exact same picture. Okay, so we have one with the star mask, so I'll just call it star mask. And the other is the main image, image 32, and we are going to do, like, it didn't remove the stars so well, but what I'm going to do is I am going to go inside color saturation here, and I'm going to like pick here, and I can see the color is in the blue here. So I am going to add some points and just like increase the blue, open up a preview and see how that looks like. So we are definitely increasing the blue around the stars, but we're also increasing the blue in between those like clouds of dust here. So let's try to just, apply that, which I think I might have overdone it. So I'll go a bit below like this. And then using pixel math, hopefully I'll be able to add back the stars. Let's see if that works. So we'll do image 32 plus star mask. And we're going to create a new image that will be RGB color. And yes, the stars have been replaced. Wow, it actually worked. It's the first time I do this. And we have like a pretty nice looking image already. And we can see a bit more like the transition between those dust lanes and the blue background there, which I really like. The next step that I'll do is I'll just do, using again the easy processing suite, a bit of star reduction. So I am going to select image 35 and we're just going to run it and not worry too much about things. So it's going to take a bit of time because it uses, again, star mask. That it will create automatically based on the image. And here we are, we have indeed reduced the stars quite a bit, maybe a bit too much, but it doesn't look bad at all. I really like this result. And we could do some more stuff. Maybe I'll do one more thing, which will be using the script called DarkStructureEnhance, which is here. And I'm gonna put it at like 0.30. We don't want to be too brutal, but we're just going to apply it, and that will make the dark structures of the nebula pop a little bit more, which is always good as well. And here we are, it does pop a bit more. I'll do a final curves adjustment, and I think we can call it a day afterwards. So let's maybe like brighten the image a tiny bit, like this. Maybe add a slight bit of saturation, like this. And I think this is a good image. Yep, I think that will be my final result, at least based on my monitor here. So that's it. So we went from scratch, from the actual frames and the calibration frames. We stacked everything after measuring everything, and then we processed it. I think this gives us a really good result. And of course, we also captured the image itself in an earlier night. So that's pretty much it. I hope it was interesting. So I'm intentionally going fast through everything. You can pause the video at any time just to give you an idea of what my whole workflow is for this kind of narrowband bicolor imaging. And I really hope it was useful. And maybe you can teach me some tips and tricks down in the comments. I had a lot of fun actually creating this image. So if you have any suggestions, please feel free to go down. If you are new to this channel, and you are not a subscriber yet, first, welcome. And also, if this is the kind of content that you like, it's not always about PixInsight, it's always about astrophotography. Tons of content about astrophotography on this channel. If that sounds like it interests you, feel free to go down, click that subscribe button, and click that little notification bell next to it. And otherwise, if you like this video, click on the like button down below, leave a comment, And as always, thank you so much for watching. Whenever you can, don't forget to look up at the stars, and I'll see you next time.